mean things about the symbol. Piggyback. Section 6. This is a section that's bounced around depending on what edition of the hands-on text you look at. Value of the function. In some editions, they'll throw this in chapter 6. At the end, they'll sort of reveal why. But in the later editions, they hold off and they say, nah, put it in chapter 7. Chapter 7, you're saying, now that you've proved the fundamental theorem of calculus, you have the definite integral. Here's a bunch of stuff you can do with it. Find area between curves, we can use that for volume, we can find the length of the curve, all this stuff. Here's another thing you can do. And so, for average value of a function, the average of n numbers is a formula most of you probably knew by the end of elementary school, especially when you became conscious of grades and you said, I got these 3 test grades, what's my test average? And then you learned how to find your test average. The average of n numbers is this. You probably wouldn't write it like this in elementary school or middle school or whatever, but that's add them together and divide by how many there are. Did you know there's a notation for this? Do we use this like in stats or something? We call it like a bar or something. Yeah. So there's another way to write this sum, of course. What if I wrote it like this? I hope that wouldn't be too off-putting. We've very recently been using sigma notation quite a lot. So man, oh man, even just talking about the average of n numbers, does it already feel like we're sort of brushing up against the definite interval, right? The definite interval always came from ugly notation that had a sum in it. And so the idea is, what if instead of just discrete numbers, like test grades or something like that, what if these were function values? So you have some function, and you know this value, and you know this value, and you know this value. You know these 5 values. Couldn't you add them together, divide by 5, and get the average of the values of the function? And so with 5, you're like, yeah, what does that really do? But what if you had like 100 of them, and then you added all those values together and divided by 100? And you're like, okay, this now starting to feel like something maybe I would care about. And so, of course, we're not going to do 5 or 100. We're going to say, well, what if we let n go to infinity and get all the function values, and we get this actual average value? Maybe that's something that will have a contextual use in the real world. And so that's exactly what we're going to do. So, you know, all of these are function values up until the nth one, the f of x of n. And so, we're going to play a lot of the same games we were playing when we were adding up areas of rectangles. We'll have some function on an interval, and then we're going to break this into n sub-intervals. And one thing back when we were adding up all the rectangles and stuff is I'd ask you, for instance, what's delta x? You remember delta x? So you say, oh yeah, the change in axis. If you're going to make the spacing be equal, that was just b minus a over n. Does that vaguely ring a bell? We've used that in a little while. And then on each of those intervals, I can pick some function value to represent the value of the function on that interval. This function value, I can pick that function value. And so this is where the star is going to creep back in, because the book says, well, it doesn't really matter how you pick that value, since ultimately we're going to go to infinity of them. There's the fancier thing with the mesh size, but on each interval, you will pick some function value. However you do that, that's what the star again represents. It could be the midpoint of each interval or the left endpoint or whatever you want to do. Wouldn't the average be this? So the question is, how can we turn this into the definite integral? Because again, it's pretty close. That would be the thing I'm after. That's the name of the section. That's the average value of the function, f, on the interval from a to b. Except n, sorry. This, just like I did over there, that's going to collapse into the sigma notation. And again, it's going to look a whole lot like something we've already been turning into definite intervals all over the place. But what's kind of missing from this? What's the thing that's missing when I did go to turn this into the definite interval?
dx.
So I have a 1 over n, which I actually don't want. I want a delta x, which is the thing that always turned into the dn. And so that's why I started you here. Do you see you could solve this in terms of n and substitute that in here, and you'll pick up a delta x. You'll pick up one other little thing, and that's what's going to show up in the final formula. But if this is true, isn't it true then that n equals b minus a over delta x? And so then won't 1 over n, the reciprocal of that, be delta x over b minus a? Again, we want the delta x. We need that if we're going to eventually take a limit. There's 2 limits you could take. You could let n, the number of intervals, go to infinity. You could do the fancy one where you have the max mesh size go to 0, and that makes all of them go to 0. You know, whichever way you want to do it, you're going to take a limit, and you need this delta x, which I can move into the sum, where usually we move things through the sum on the outside. We're going to move it in there, and this whole thing is going to become a definite integral. It's going to become the integral from a to b. There's a dx, and unlike the awful formulas we saw in section 4 and section 5, what's the integrand, everybody? F of x. Hey, isn't that nice? There's just one bonus thing we pick up. Outside, there's still a 1 over b minus a. This is the average value of a function. And when you step back from the derivation and all the terrible notation and the dot, dot, dots and all that nonsense, this should kind of make sense to you. The definite integral from a to b is sort of adding up all these things, and then we want to divide by like how many there are, kind of. This is actually almost literally another formula that I've shown you. And again, is the reason Anton used to put it into chapter 6. Does that look familiar at all? I'm going to show it to you. Because it's not a formula I made a huge deal of in chapter 6. It was on a day where I showed you a ton of things, and I said, gosh, you know, each one of these things is sort of important, but it's funny, this one is perhaps one of the least important. Do you remember that there is a thing called the mean value theorem for integrals? It's not heavily represented on the AP exam. The first mean value theorem, that's the right one. This one, though, the whole idea, again, is if you have an area under the curve from A to B, the blue stuff, the mean value theorem for integrals says as long as the curve is nice, then there has to be some rectangle with base b minus a that will have the same area. And there has to be a value x star. Instead of c, they use x star here because we're in integral land. There has to be a value x star such that f of x star is the height of that one giant rectangle that'll have the same. And so if instead of calling this the average value of the function, if I call this f of x star, do you see it's actually the same formula? Look, here it is. When we used to do these problems, you would find the blue stuff, and then you would say, okay, the base of the rectangle is b minus a, the height of the rectangle is f of x star, and then you would go and solve for x star. The mean value theorem for integrals guaranteed that there would be at least one x star such that blah, blah, blah. And so this is the same thing. And so again, in previous editions, they stopped right here and they're like, hey, this is basically how you find the average value of a function. And now they hold off. And so chapter 6 is pretty stuffed full of things. So I guess it kind of makes sense to pull it out. But anyway, that's it. Let's do one example real fast, just so you can see you're going to Set it up basically exactly the way you want, and then I'll show you an AP problem where you'll start to see, as we head towards May, like through the second semester, we have to look more and more at these AP problems and all the various ways they ask you about this kind of thing. But sure, there could be some multiple choice question like this. Find the average value of y equals root x on 1 to 4. You can't make it any more straightforward that you're going to use this formula. The big careless error students always make is they forget to divide by b minus a. Like they know, oh yeah, I just have to anti-differentiate f of x. This is great, and they forget to divide by b minus a, so don't do that. But other than that, this is relatively straightforward. Let me find the AP problem. This is great. Franklin's recording all this. Now next year, if I teach this lesson again, I don't know how to do it. Just post the videos. I already did this. Let's see. Did you do 1 over 4 minus 1 antiderivative 1 to 4 of root x dx? If you wrote that on your paper, you set it up right, then it's just, again, can you execute a definite integral? You have to do some number of them on the test. And just final exam, I didn't want to analysis. Did you get 14 nights? So, if not, that's the thing you have to practice. So again, what does that mean? Like, what's the number we found? So you have root x from 1. This is the point 1 comma 1 to 4. This is the point 4 comma 2. And so sometimes the y value is 1. Sometimes the y value is 2. Hey, if it was a linear function, what would the average value on that interval be, everybody? 1.5, right? Like halfway, but it's not linear, it's curvy, and that's what makes it complicated, and that's why we need a definite integral for things like this. So the definite integral is kind of taking all these y values, adding them together, and dividing by how many there are. Again, sort of, but there's a limit that makes it all happen, right? There's the limit technology in the background. It's not discretely doing that. So let me show you, as a closing thought here, the BC exam from 2011. Found this good problem that has 2 things in it. So here again, I think I've already shown you 1 or 2 problems like this from previous exams where there's a table of data, and hey, really quickly, everybody, do you see what's happening here? What's not happening, I guess? They're not like evenly spaced, and so that's why we talk about that as stars and everything, because often in the real world, when you get actual data, sometimes you don't have it at like the same time intervals, and yet you can still play calculus games with it. I love the scenario. As a pot of tea cools, it's very nice. The temperature of the tea is modeled by a differentiable function h for these time values where t is measured in minutes and it's measured in degrees Celsius. So I don't know where this is. Maybe in England because they drink a lot of tea. Values are shown in the table above. Okay, so check this out. Part C. This goes back to the end of chapter 6. They're saying, what's the antiderivative of h prime of t? Do you remember? I tried to already start making a big deal of when you anti-differentiate a rate of change, what are you getting? The net change. And so again, if they say using correct units, explain the meaning of this in this context. And so what this is the net change of the temperature of the T in degrees Celsius from time t equals 0 minutes to t equals 10 minutes.
If you write that dumb little sentence on your paper, the AP score is like, this person knows a bunch of calc. And hilariously, they ask you to evaluate it. I think I showed you one like this before. Hey, everybody, what is the net change in the temperature of the tea? Negative 23 degrees, right? 43 minus 66. Another way to think about it is the tea has cooled by 23 degrees over those 10 minutes. Yeah? And so, again, hilariously, on the AP-BC test, you have to subtract two numbers and you get one of the 2 points. But it's still pretty fancy because you have to be able to read this. Okay, so now look at part B. You see how it's not h prime of t? But now there's this bonus fraction hanging out on the front. So, what's this, everybody? The average temperature of the tea from time t in degrees Celsius from time t equals 0 minutes to t equals 10 minutes. And so they say use a trapezoidal sum. What's that? I showed you left endpoint sum, right endpoint sum, midpoint sum. I have not yet shown you trapezoidal or Simpsons. And so come back in the second semester and I'll show you those. How fun for you. So there's like basically one more big one that we have yet to learn. So, okay, that's all I got. Go use your time wisely, do some homework. Thank you, seniors. Hope you had fun. Right? It's kind of weird being video recorded.